3.4, vectors and dot products. So when we're talking about vectors, we can add, we can subtract, and we get another vector. We can do a scalar multiplied in a vector, we still have a vector. Now we have what we call a dot product, when we actually multiply two vectors together. In this format, we would take u times v, and it will give us an actual number out. So when we multiply two vectors together, we get a scalar answer, meaning we get some number answer. So when we multiply two vectors together, in this case, we take our u value, which is our first, and our v value, which is our first. So if we do 8 times 2, that would give, 4 times 2, that would give us 8, plus 5 times 3 would give us 15. And again, we have a scalar answer. So now we add those two together. Our answer here would be 23. I want you to pause the video and try to do B and C by yourself. And you should get 0 and -6. So now when I'm looking at my dot product, now this is where you have to be a little bit careful about what our answer will look like. So first, if I look at this uv, I'm going to first find the dot product of u times v. So u times v are these first two. This is going to be -1 times 2 plus 3 times -4, which would give us a -2 plus -12, which gives us a -14. Now this is where this right here is a vector. Notice how there's not a dot there. That's not a dot there. This is saying -14 times our u or w vector 1 comma -2, which would give us an actual vector answer, which is -14 positive 28, because I would multiply that into both of them. Whereas here, one thing we can do, because we already have this, multiplication, because right here it's multiplying, you could do this first and then do the dot product, but we also can take out this 2 and have this dot product that we already found. So because this is a dot product multiplied, this becomes 2 times our -14, because we just found that right over here. So this answer would give me a -28. Again, if you found this in a different format by first multiplying the vector by 2 and then doing your dot product, you should still get -28. Now I have our magnitude of u. So we already have our vector component. So this would be the square root of our -1 squared plus our 3 squared, which becomes the square root of 10. Now one thing that's important to know that we also have, we have a rule that our magnitude squared is equal to the dot product of itself. So let's say if we found the dot product of u, which we could do that, so -1 times -1 plus 3 times 3, that will be equal to 10. So if I were just finding the magnitude, taking the square root of 10 is going to simplify or give us this rule. So let's say if we have the angle between two vectors. We do have other formulas for when we just have the length, but now because we have vectors, we have this dot product rule if we want to find the angle between two vectors. So that would be the dot product of u times v over the magnitude of u times the magnitude of v, where the angle would be the cosine. So you'd have to take the arc angle of that. So if we apply that formula to this situation, we can have our cosine of our angle. So again, this is our dot product of our u times v divided by our magnitude over u times our magnitude of our v. So if I simplify this, we would get that this would be, I can take out a 25, so 5 squared root of 34. Now that's right here, cosine of the angle is equal to this ratio. So if we want to get that angle by itself, we can do the arc cosine of this ratio, and we would get that the angle is 0.3869 in radians, or 22.1663 degrees. That's an 8. So now let's say if we are going to be rewriting something. So a couple of things when I'm looking at my dot product. This right here, orthogonal, is kind of like the same thing of thinking perpendicular. So when we're looking at two vectors that could be perpendicular, this will only happen if the dot product between the two is equal to 0. So looking at this right here. So this expression right here is just the same thing that we used over here. It's just moving that divide by magnitudes over with our cosine. So why would we want to do that? Well, if we know that the dot product right here is equal to 0, then we know that it's going to be perpendicular. So if I want to see if this is going to be perpendicular, I'm going to find the dot product between u and v. I want you to try to pause the video and find the dot product between u and v. And you should have gotten yes. Yes, it is. Because they are perpendicular, or when we're talking about vectors, orthogonal. Now this is where we start talking about applications again. So when I talk about our applications, this is like the essential math of physics. How can we get physics or moving components or be able to fly into space? Well, it's the math with vectors that help us get us to that component. So we have two different things. We have a projectile component. So when we have a projectile of a v onto u, this is the formula that we're going to be using. Or if we have a definition of vector components, we can also use this definition of vector components for our projectiles. So let's say we want to find the projection of u right here onto v right here. Then write u as a sum of the two, let's say perpendicular vectors in this format. So first, we're going to write this W1. It says first find the projectile of u onto v. So this would be the projectile of u onto v. Kind of looks like a logarithm, but it's not. U onto v, so this is where we're using this right here, equation. Then I'm writing down that equation. This is u times v, that's u times v, divided by my magnitude squared. If you remember what I said earlier, our magnitude squared is going to be the dot product of that vector. So in this case, the dot product of v would be 6, 2, 6, 2. That whole thing multiplied still by a vector 6, 2. So essentially this whole thing becomes 8 over 40, because remember this is a scalar, a number divided by a number, that's 8 over 40. Now if I multiply that in, this new vector is 6/5 and 2/5. Okay, so that's the projection of u onto v. Now the next thing we need here is our W2. So when you're looking for our W2, so that reminds me of taxes. So we have our vector u subtract our vector w sub 1. So that's taking our u, subtract our w1, so now this is our w sub 2. Now then it's saying write u as a sum of two perpendicular orthogonal vectors, one of which is the projection of v to u. So again, that's that w. So if I want to write our sum of our two, so if I add these two together, I would get that 6/5 plus 9/5, that's these two, plus 2/5 plus negative 27/5 would be 3 over negative 5. Oh, look at that. Isn't that great? Why, Mrs. Frickman? Whoa, why are we going to do something like that? To help us figure out a problem like this. Look at this question. A 200-pound cart sits on a ramp inclined at 30 degrees. Remember that force is gravity. What force is required to keep the cart from rolling down the ramp? So first, again, this F, because it's straight down, that's our force of gravity. It's telling us the 200-pound cart because that's the weight, and that's gravity pushing it down. That means, again, because it's down, this would be like a negative 200. Because it's only moving down, that's where we're only using our J component. So F vector would be negative 200, 200J, because there is no I, because there's no horizontal movement. So now we have to figure out our vector v. So here's my 30 degrees. If I'm looking at my vector v, remember that's going to be our cosine of our angle. So cosine of 30 degrees I plus our sine of 30 degrees j. Because we are smart individuals, we know cosine of 30 degrees using our special right triangle is square root of 3 over 2i, and sine is our 1/2 j. So if we're looking at our vector v then would be square root of 3/2 and 1/2. So now we're looking for w sub 1, a projectile of f onto v, of f onto v. So using that formula, we can write down And if we simplify this all down, then we get negative 100 here over 1, that's this right here, times our V, which would be equal to, but it's asking what force is required to keep the cart from rolling down the ramp. So in this problem then, when we're looking at our W sub 1, to keep the cart from rolling down the ramp is this negative 100. That's our magnitude to keep this cart from rolling down the ramp. So when we're talking about negative, that just means it's moving down. That means we need 100 pounds to keep it from rolling down the ramp. And last but not least, we have talking about work. So force acts along the line of motion. So in this case, if you're pushing something this way, you're going to have that force. If you have an axis of an angle projected onto a line, obviously the force is going to be needed in a different direction. So when we look at the definition of the work done by constant force F as a point of application moves along the vector PQ. In either the format work is equal to the projectile of force projected onto the given form with the magnitude of PQ, or the force times PQ. So to close a sliding barn door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Find the work down in moving the barn 12 feet to close the positioning. So this is kind of a picture. You have to pull on this rope at 60 degrees right there. This would be the force in which you're pulling. How much work is needed to do this? This is also kind of like the projection of force onto this PQ, because we want to try to shut this barnyard door. So we're looking at this first, work. So we are using this equation, work is equal to. So if we have the projectile of F onto PQ, times PQ. We can also rewrite this right here as the cosine of my angle times the magnitude of F times PQ. So if we are looking at that, we can look at a cosine of our angle, cosine, which would be 60 degrees then, with our magnitude of F, then our magnitude of PQ. And the magnitude of F is this force, the magnitude of force that is used. Well, it told us it has a constant force of 50 pounds. We can have our cosine of our angle 60 degrees with our magnitude of our force is equal to 50, because we're pulling at this at 50 pounds at a constant angle of that 60. And our PQ, our magnitude of our PQ is this length right here, which would be our 12 feet. So if I multiply that all together, I would get roughly about 300 foot per pound is needed. This is how much work is needed to actually do this by shutting this barnyard door. Well, that's what we got here. I know it's very complex, but we will work through every problem that we have within class. So make sure you come and ask questions. Have a wonderful day.